Yeah, thank you for the introduction. So I want to share about the technology related to predictive analytics and predictive maintenance and how it can be used to improve your maintenance activities and your overall efficiency in your production plants and manufacturing or other environments where you manage your assets. So yeah, usually the key is to focus on some business objective where there's a good value in improving your maintenance and monitoring your assets and taking care of your assets. So that can be avoidance of unplanned breakdowns, reducing maybe unnecessary maintenance, maybe extending your preventive maintenance schedule, as well as for manufacturing applications relating the process conditions to quality and ultimately reducing scrap or improving quality. So keeping those objectives in mind, then you'll kind of tailor the predictive solution for those purposes, whether it be early detection of symptoms that your machine is heading towards a failure, maybe diagnosis of the problem so you can have a shorter time to repair your equipment, as well as relating the process to quality and the quality prediction as well. So the business objectives also kind of drive the configuration of the templates for the predictive solutions. So yeah, if you go on to the next slide, and this really highlights the value of the solution if used correctly and configured properly. For example, 1 minute of downtime, for example, in automotive factories as example, can cost tens of thousands of dollars. So if you predict and prevent one failure, and that one failure causes an hour of downtime, you're looking at hundreds of thousands of dollars saved by having this predictive solution up and running and used properly. So the general idea is that keeping in mind the business objectives of improving your reliability or improving your stability in your process, the predictive maintenance can really improve your asset health and your management of your assets, as well as if your quality is your focus or objective, it can also be used to improve your part quality as well as reduce defects and scraps as well. So the PDX software is up and running in many organizations and manufacturing as well as fleets and so on. And this is an example of the templates for manufacturing applications. So you'll notice that there's already 10 or 15 templates listed here. There's maybe a total of 25 or 30 different templates. And if you just look at the different ones available for the manufacturing, these include predictive monitoring of industrial robots, predictive solutions for machine tools, including the spindle bearing, the linear axes, as well as coolant and so on, as well as additional use cases on stamping and also auxiliary equipment like compressors. So this is one of the nice things about the PDX software is that these templates are already available. So the ability to quickly configure them and deploy them for your particular application is much faster than what you may find in some other solution offerings. So when we say a template, what we actually mean is actually the entire recipe of how the solution is configured. And this is a good illustration of the 6 steps in the template. To include what data, what sensors are needed, how to gather the data both from external sensors and from the data from the existing sensors from the PLC or the control system, as well as what sampling frequency and other aspects of the data collection we need. Basically, we want to collect the right data at the right quality to meet our overall business objectives. And then from there, the template also includes how to process the data, how to filter the data, as well as how to extract features or patterns from the data. Conditions, that reference condition may be baseline conditions from the machine or when data was collected. And by doing that comparison, you can set process health over time. You could track if key only is a problem developing, but is that problem developing when a site might occur, so that maintenance action and more proactive, as well as you can take additional steps to diagnosis. This shows the general framework of the templates and how the 6-step process is used. And one of the nice attributes about it is that the PDX software is already integrated into the Beam software. So once we find early symptoms of machine failure, we can send work orders and other information so people can then address the maintenance issues ahead of time and be more proactive with their management of their assets. So with that, template in mind, the next slide will show the corresponding technology and aspects around it. So you'll notice that the PDX DAC is our dedicated software for the data collection. The sandbox is what we use for configuring the templates and the predictive analytics. And then we also have the deploy software as well. So this one kind of goes into the three-step process, or the three softwares. The DAC is for the data collection. Our sandbox software is where the templates lie and allow us to quickly configure those analytics and templates for different industrial equipment. And then once that configuration is finalized, we send that to our deploy software, which then runs the calculations and has a really easy and intuitive interface to visualize the results. And that's also where we connect to the Beam software as well. So this kind of gives you a high level of the motivation, the different steps in the process, as well as the software. And I think the next slide, I'll hand it over to my colleague Mo, who will talk a little bit more in specific about the use cases and also a demonstration of the technology.
Thank you. Thank you, Dr. Siegel.
Thank you so much, David, for the introduction. And Kevin Kursad, I hope you can hear me fine, right?
That is perfectly fine, Mo. Please,
Thank you
go ahead.
so much.
Thank you.
So I want to follow up and continue from David's conversation, and I want to show several case studies of how predictive analytics is deployed in a real environment. And if we proceed through the animation, you're going to see that we have two domains of experience. On the left side is our core domain. So most of our projects are conducted inside the factory. So as David mentioned, we have over 25 solution templates, including robotics, stamping machines, CNCs, and so on. And the idea here inside the plant is to significantly impact the OEE calculation. So OEE is overall equipment effectiveness. And by bringing predictive maintenance, we are able to maximize the uptime in the facility, maximize the availability of the machines, which is a critical factor of the OEE calculation. And at the same time, by using predictive quality, we are able to make predictions of when a specific part is going to be a bad part on the machine. And therefore, we can significantly reduce scrap. And adding to that, on the spare parts side, by integrating to a maintenance system like Beam from BIMSR, we are actually able to predictively replenish spare parts. So before the machine actually fails, we could send information to Beam to request a new spare part, for example, to be shipped to the machine before the machine actually fails. So just imagine reduction in spare part inventory and also reduction in the labor time to fix the machine, because we are telling a maintenance system like Beam that there is a specific machine, a specific component to fix, a specific spare part to be ordered, and also optimizing the PM schedule, which is available in the Beam software. So this is a closed loop system that enables the maintenance system and the maintenance process to be conducted in a better way. On the right side is what we call smart product. So if you do not manufacture parts, but you monitor or use parts in the field, so the audience here is your actual customer, your end user. Let's say you make a machine tool, or you're making a pump that is used out in the middle of an oil rig, for example. So here the business case is different. We're using analytics to remote monitor, to predict issues, and to diagnose equipment that is owned by the OEM in the field, okay? And in return, the OEM is offering these analytics as a subscription or as a service to their customers, okay? So ensuring that their customers are satisfied and the maintenance activities can be governed by a system like Beam, so that the oil pumps in the field or whatever product you manufacture can be monitored in a predictive way. Closed loop design is very interesting. This is actually feeding data back to the designer of the product. So not only are we looking into manufacturing or looking into the aftermarket service, but we're doing the whole digital thread of the product. We are actually sending data back to the designer so they can improve future generation or future designs of the product. Next slide, please. So I want to show two quick examples. The first example is on the smart factory side, looking at robotics. If we go through the animation, David started by saying there's a huge business case in the automotive industry. And this is actually a business case calculation for a large Japanese automotive OEM. Just, in a typical factory, 500 robotics, the average minute of downtime of a robotic is almost $10,000. I mean, I think that number has recently increased as the automotive industry is becoming more and more conservative. But if you notice, robots don't fail very often. There's only about 30 robot failures every year. But each robot failure can actually lead to 30 minutes of unplanned downtime, which is almost $300,000 for the robotic failure. That's a significant amount of lost and unplanned downtime. And with a predictive system, it is difficult to predict all events. But if we only predict 50% of issues or events that are occurring, we can actually save this OEM. And in fact, we have saved this OEM almost $4.5 million per year by just predicting 50% of the failures on 30 robot failures. So the ROI can be significant just by looking at the uptime. This is an example of a realization, actually. We will show it later in a real demonstration, but the system has to be very user intuitive. The main users here are the maintenance organization in this case. And the maintenance people, they are not PhDs and they are not data scientists, and we don't expect them to be that. So by looking at something like this, you're able to immediately look at the health of the machine. Very intuitively, you can see a degradation. You can see the machine's health has entered a warning, which is shown in yellow. You can see a prediction with a prediction window, plus or minus. And you can actually, if you click the animation, you're going to see joint 5 at the bottom. That is actually the specific issue on the machine. And that's the type of information where we can close the loop with a maintenance system like Beam and inform Beam or the maintenance system that there is a prediction of failure on joint 5 in the next 2 to 3 weeks, so that the PM schedule will be automatically optimized, the labor to fix the machine will be scheduled, and also the spare part will be ordered. So we're moving immediately from a fail and fix approach to a predict and prevent approach, in this case on a robotic inside a factory. The second use case here is with a large heavy industry manufacturer of tractors and excavators, right? So in this case, I'm not monitoring robots inside a factory. I'm monitoring components on a big truck, which is sitting in the middle of the desert, for example, doing mining, right? It is very costly to send somebody out in the middle of the desert, in the middle of the night, to fix the engine on this machine, right? So predictive analytics even has a stronger business case here. So just imagine if you click, you're going to see a visualization of the different mining sites that Komatsu has, in this case in the Canadian peninsula. And you're going to see that there's 4 mining sites. You're going to see color coding where green is a healthy mining area. Yellow, there's a degradation on some of the tractors. Red, there is a potential failure on some of those mining trucks. And other colors can be also configured. You can see at the bottom there the different components of the mining truck that are being monitored in real time. So in this case, a solution like Beam could be used to monitor the maintenance activities of smart products that are available around the world in order to ensure that this product, whether it's a Komatsu engine or whether it's an aircraft engine, that this product is running all the time and that spare parts are delivered to that product before the product fails. Because the cost of failure here is significant, and the cost of getting somebody out there with a spare part could actually be extremely costly for the environment. So if we go to the next slide, you're going to see a simple visual, actually, of the different mining sites. In this case, there is one huge mining area, Canada, for example, with 3 mining sites, and you can immediately see green, yellow, red. What is healthy, what is degrading, and what is failing. And if you click once, you're going to see a zoom in into one of the mining sites where you can immediately see that the diesel engine in this case is actually the biggest issue that is happening on this machine. So a system like Beam would be informed that the diesel engine is having a problem prior to the failure. So a new component of the diesel engine would be dispatched with a maintenance person to the remote location of the truck in order to fix it before it actually fails. So these are some of the case studies, in Smart Factory and Smart Product that we're able to realize with a very closed loop system that is collecting the data, analyzing the data in real time, predicting issues, and then sending that information to a real-time system like the Beam engineering asset management system or enterprise asset management that enables optimized scheduling and optimized spare part replenishment to the environment. And if you allow me, I can just show a very brief demo just to give you the feeling to the team on the call. If you could see my screen, I want to show a very simple demonstration of a robotic factory, for example. So you notice this is a cloud-based solution. It could also run on-premise. And as a maintenance person, I can very quickly see green, yellow, red. I don't need to be a data scientist. I don't need to have an advanced degree. It's a very intuitive approach, like a traffic light, green, yellow, red. And here's an example of a healthy machine. This machine is actually performing very well. The health values with the artificial intelligence and the machine learning running in the background, those health values are close to the baseline, which is green. And as it degrades, it'll start veering towards warning and veering towards red, which is a failure threshold. And the AI is actually able to self-learn statistically what those thresholds are so that they can be adaptive to the changing dynamics of the process, right? Here you see, this is data actually from an automotive client that they allow us to show for offline data. And here I've hit degradation. So very quickly, I can actually deliver a prediction for this robotic where at least 2 to 3 week window I have here from October 16 all the way to December 11 to do different things, right? I can send out predictive alerts, which will be sent out prior to the failure through the Beam system. We could request a new spare part. In this case, spare part for joint number 5 will be automatically replenished through the Beam system. And I could also optimize the PM schedule so I can find a specific person who knows how to fix joint 5 through the Beam system and bring that person out to fix the machine in time, right? So the idea here is we want to maximize the uptime. We want to sustain a very high level of uptime in the manufacturing facility. And we want to make sure spare parts are optimized, and we want to make sure the efficiency of the preventive maintenance process is optimized as well. And as I mentioned, we have over 25 solution templates. I mean, if you look at a CNC machine, we're looking at spindle bearings, we're looking at ball screws, we're looking at the coolant and the alarms. This is an example of a bearing where the predictions here are actually curvilinear in nature. So our analytics recipe that David has shown is able to combine different machine learning algorithms together, and the templates like this can be deployed in a matter of weeks, okay, and integrated in weeks with the Beam solution, so you can have a predictive enterprise asset management system running in weeks, delivering value to your company, right? So with this, Kursad, I'd like to hand it back to you, and thanks for the opportunity.